All right, we have made it. It is our last section in chapter 15, minimum and maximum problems. We're going to see a lot of familiar things like critical points, local mins and maxes, maybe some new things like saddle points, but again, also some slightly familiar things like the second derivative test. So again, let's start like how we've been starting and take a look at a function in 2 dimensions. So if we have our function f here, some points of interest on this would likely be point A here and B there and C right there. And A and B would be of interest because those would be places where we would have horizontal tangent lines. So our derivative would be equal to 0. And our spot here at C would be a place where that derivative is undefined. Right? Anytime we've got a node or a corner, um, a cusp, that's the word I was looking for, those fancy math words. So anytime we take that sharp corner on our function, we've got a place where we could have a possible min or a max. And we can classify these like A is a local max, B is a local min, and C would be our absolute max. So remember when we say the word local or relative, that's the other word sometimes we use for that. That means, sort of basically relative to the points nearby. And so when I'm teaching 251, I always talk about a local or relative max at like in our classroom, there is the tallest person in the room. So that person probably is not the tallest person in the world, but locally to us in that room, that's the tallest person. It may not even be the tallest person on campus. So we could also kind of look at that way. If we restricted our domain to just the people on campus, there would be some absolute max of the tallest person that's on campus. But in our classroom or wherever we are at any given time, there's probably a tallest person in the area. And well, there is a tallest person in the area. Maybe it's actually you. Um, and that would be your local max. And then that absolute or global min or max, that is the largest or smallest value. So that is the largest person or tallest person in the world or in the room or on campus, whatever you want to say your domain is. So we're going to be looking for similar things in R3. We can have absolute mins and maxes like we see on that graph right there. We've got that very, very highest point, very, very lowest point. We can have local mins and maxes, so you can kind of view that like a local max would be looking at like Mary's Peak if we're here in Corvallis. Locally, that's the highest point. But, we could then, expand our view and go, well, if we got a little bigger and included a little more of Oregon, Mount Hood, that's taller. So maybe if we, made an area where that's the tallest point, that would be our absolute maximum. But if we, then expanded it to look at more of the country or more of the world, that still would only be a local max. And then our highest peak in the world, that would be our absolute maximum. So it kind of depends on how you define your domain. If you restrict it or make it to be anything, infinity to infinity or the whole world. Um, and so we've got these definitions here. They're little, I even kind of trimmed them up a little bit, but they're sort of our fancy math definitions. But if you've got that idea that something that's a local min or max just means really for the points right around it, and absolute mins or maxes are the highest point or the lowest point of our function on its domain, then you're good. So critical points, we're still going to be looking for the same things really that we were looking for in R2. We're going to be looking for, when those first derivatives, and we're going to look at the partials with respect to x and the partial with respect to y, when are both of those equal to 0? And we need for both of them to be equal to 0, not just one or the other. They both have to be 0. Or we want to look for any places where we have those partial derivatives that might be undefined. So that was normal. We're going to have, just like last, in 251, when the undefineds didn't come up very often, they're not going to come up very often here either, but it is something to be aware of, something to watch for when we've got, say, rational functions, when we've got something where the denominator might be 0. All right. So saddle points. This is a, probably new situation that we've got here in R3, but maybe you've seen this before. So a saddle point is where we've got, if we look at the partial derivative with respect to y, that's, I guess, what I started drawing here. If we look at that trace there, that's a parabola that's got a minimum. And there at 0, 0, it's, going to have a place where that partial derivative is equal to 0. But then if we look at the trace in the x direction, it is an upside down parabola, and that's going to have a maximum. So both of those partial derivatives at 0, 0 are going to be horizontal. They're going to be 0. But because one's a min and one's a max, it's neither a min or a max. It makes this sort of like hybrid point, which is a saddle point, and we call it that because it looks like a saddle for a horse. So we will see quite a few saddle points. I'll show us an example of a function that's got, a min and a max and a saddle point, or a min or a max. I think I only have one or the other. So how are we going to find these points? So again, we're mostly going to be looking for these places where our partial derivatives are equal to 0. So we're going to start there, and then we're going to look at this thing, which we're going to call capital D here. And we're calling it that for a reason that will become very clear here in a second. Notice it has to do with our second order partial derivatives. So our partial with respect to x twice, our partial with respect to y twice, that's being multiplied, and then we've got subtracted, our partial with respect to x, then with respect to y squared. So the question is, where does this come from? Where it comes from is us taking the determinant of our second order partial derivatives. F of y. There we go. And the way that you can look at this matrix that I set up is that our first row is x and our second row is y. Our first column is x and our second column is y. And the rows are telling us what derivative we're taking first. Our columns are telling us what derivative that we took second. And if we take the determinant of this, remember that determinant, it's been a little while. We did this with cross product. We multiply those diagonal elements, and so we get f of xx times f of yy minus f of yx times f of xy. Now, if we remember another thing from a little earlier in this section, that those second order partial derivatives, when we take it with respect to x and then with respect to y, or vice versa, those two are equal, right? F of yx equals f of xy. So I could rewrite that, so leaving the first part alone, we could rewrite that as just f of xy times itself, so f of xy squared. Notice that's exactly what's sitting right there. So that's a determinant, and that's why we call it capital D. So if D is positive and our second partial derivative with respect to x is positive, then we have a local max. So remember that second derivative, that's looking at concavity. So if you think about something, or local min, did I say max? I might have. If we're thinking about concavity and we're thinking about sort of that parabolic bowl, that's a nice quick little example to think about. It's concave up, second derivative would be positive, but we have a minimum. So same idea, if that determinant is greater than 0, so it's positive, but our second derivative with respect to x is negative, then we have a max. Okay, so again, that's sort of looking at this situation here. Really bad pictures there. If that determinant is negative, then we have a saddle point. So that's easy. We don't even have to look at what that second derivative is with respect to x. If that determinant is 0, then our test is inconclusive. We have to do some other things. Maybe we do have to graph it, maybe look at it a little more. So hopefully we won't get it that it's equal to 0. All right, let's do a couple of examples here. So now that we've got our function here, or our surface, let's find the critical point or points. I do think it's only one in this case. So we take those partial derivatives with respect to x and then with respect to y. Then we need to find out when both of these are 0. They are both 0 when x is 0 and when y is 0. So saying it that way helps us realize, okay, it's got to be at the point 0, 0. So that partial derivative with respect to x is 0 anytime x is 0. And so y could be whatever we want, but as long as x is 0, our partial derivative with respect to x is 0. But we're looking for that place where both of them are equal to 0, and they're only both equal to 0 when x is 0 and y is 0. So that's why it's that one single point. So now we need to look at that second derivative test. So we need to find that second derivative with respect to x, that's second partial derivative with respect to y, and then our f of xy. So let's see, f of xx, that's going to be -2. F of yy, that's going to be -2. F of xy, that is going to be 0, because again, we're looking at this partial derivative, and then we're going to take the derivative of our -2x with respect to y. X is a constant, so it's like we have two constants there multiplied together, so we're going to get 0. So that determinant, our capital D, is -2 times -2 minus 0, so it's 4. So what this is telling us is that that is equal to 4, which is greater than 0. Cool. So we have either case 1 or case 2. So we need to look at what our partial derivative with respect to x twice is. It's -2, which is 0, or which is less than 0, excuse me. So that back here is, now that's case 2. So that tells us we have a local max at 0, 0. And I think I graphed these. If we go into Safari here, nope, that's not the one we want. We want to look at that one. There we go. There it is. And yeah, we sure do. At 0, 0, the output is 9. And we can see we do have a local max. This one actually is a global max, but we for sure have a local max that is, at least for the points right around it, it's the highest point on our graph. And the actual maximum value is that value that we get from plugging 0, 0 into our function, which in this case is 9. Let's look at another quick one. Whoops, I forgot to change the function on this. So I will do it on the notes, but what we actually want to look at is not the same function. We want to look at xy minus 1/3 x cubed minus 1/3 y cubed. So we need to start out the same place. We need to find those critical points. So we need to take our partial derivative with respect to x. So we're going to get y minus x squared, right? Because that first term, the derivative of plain old x is 1. So we're going to have our y there, which is a constant. And then here we're going to get 1/3 times 3x squared. So that's going to be x squared. F of y is going to be extremely similar. And we're going to get x minus y squared. Okay, so again, we need to figure out when are these equal to 0. When are they both equal to 0? So what you end up with these critical points, and when we're figuring out when these partial derivatives are equal to 0, is you've got a little system of equations. We're trying to figure out what x and y values we can plug in that make both of these things 0. So this first one tells us that y is equal to x squared. This one tells us that x is equal to y squared. So you can take one of the two of these, it really doesn't matter which one, and plug this into the other one. We can do substitution, is the fancy, our actual math name for that. So instead of y equaling x squared, we're going to put y squared in there, squared. So we'll have 0 is equal to y to the 4th minus y. 0 is equal to y minus y cubed minus 1. So we are found here that this is true when y is equal to 0 or y is equal to 1. So take your cube root here, cube root. So now what we need to do is go back up here and say, okay, if y is equal to 0, what does that mean for x? X is also going to be 0. So 0, 0 is one of our critical points. If y is 1, what does that mean for x? X is also 1. Doesn't always happen this way. But we get 2 critical points. So we have 2 things that we need to take a look at and see what's happening with those 2 points. So again, we've got to go to that second derivative test. So what we need to do is find those second order partial derivatives. So f of x. Let's see, derivative of y is going to be 0 minus 2x. F of y is going to be, let's see, derivative of x is 0 minus 2y, and f of xy is going to be 1, because the derivative of y is 1, and then the derivative of x squared is going to be 0, because that's going to be a constant in this case. So that determinant d in this case is going to be negative 2x times negative 2y minus 1. So let's see, we're going to get 4xy minus 1. So let's look at what happens with 0, 0. So that determinant at 0, 0, that's going to be negative 1. So we get a determinant that is less than 0. Let's go back to our, oh, that is case 3. That's right here, when d is less than 0. So that's telling us that we have a saddle point. Interesting. Okay. It's going to make an interesting graph to look at. Good. And then 1, 1. So let's look at that determinant at 1, 1. We're going to get 4 minus 1, which is 3. So that's greater than 0. So we have to look at our partial derivative with respect to x, or second order partial derivative with respect to x. I always forget that second order part. That's going to give us negative 2, which is less than 0. So when the determinant's greater than 0 and the second derivative is less than 0, this means that we're going to have a local max. So let's take a look at this graph really quickly. That's the one I actually started on. All right, there we go. Oh, yeah, we can hopefully see it here. Scoot that up a little bit. There's our maximum point at 1, 1, and then you can see our saddle point. And so it looks a little different there, but yeah, we're getting that saddle point there at 0, 0. All right, very cool. So some of these will end up with some fairly intense algebra. Ooh, did get it spinning here when we're finding the critical points. So that's what we'll work on spending most of our time on in class is what do we do when we get a little bit more intense algebra, a little more than what we have here on these 2 examples.